I'm Ken Hamilton with Biominerals Technologies in Millville, Utah. Our presentation today is on creating CO2 or carbon dioxide to maximize growing systems. We have created this video presentation with a table of contents, but also a content index information locator so that you can watch the entire video right from the beginning, or you can go to any segment or subsegment of the video, click on the link, and the video will start at precisely that location on the information you're looking for. This presentation is on the importance of CO2 in plant production. And while it is not listed as an NPK type requirement, it is without exception the most critical and important nutrient in growing plants and producing yield. CO2 is more important to high yield potential than N or any other mineral element. At first, that statement seems out of place because the fertilizer and chemical industry has strongly instilled in our farming consciousness that NPK is what matters in agricultural fertility. Rarely will you ever hear any of them talk about the atmospheric gases. Well, when you look at a plant's dry matter weight, let's see what it's actually composed of. Carbon, 45%. Oxygen, another 45%. Hydrogen is at 6%, and nitrogen between 1 and 1.5% of the plant's total dry matter weight. Carbon, oxygen, and hydrogen are atmospheric gases. Nitrogen is also an atmospheric gas. There's 37,000 tons of nitrogen above every acre, but it's not in a soluble form. Elemental carbon, elemental oxygen, elemental hydrogen, and nitrogen are not plant available. Yet these make up 97.5% of the plant's entire dry matter weight. With these being so much of the plant's dry matter weight, how do we get them from an insoluble elemental state into a plant? Well, that's called the process of fixation. Carbon and oxygen have to become carbon dioxide, CO2. Oxygen can be fixed into water with hydrogen or with nitrogen as NO3 or nitrate. Hydrogen can get fixed with oxygen to make water or with nitrogen to make ammonium. And of course, nitrogen, we have it available in a fertilizer form, but it is also fixed by beneficial microbes such as rhizobium and azotobacter. They will take atmospheric nitrogen and fix it for the plant. These atmospheric elements make up 97.5% of our plant's dry matter weight. Our soil elements, magnesium, potassium, calcium, phosphate, and sulfur, make up approximately 2%. And so we have 9 elements that make up 99.5% of our plant's total dry matter weight. The other 0.5% of our plant's dry matter weight are trace elements. These are enzyme activators for not only microbes and insects, but plants, animals, and mankind. Enzymes require trace elements to activate and function. And so it's that broad spectrum group of nearly 70 or so trace elements that now act as enzyme activators. All plant, animal, biological life, human life, all come with enzymes. They don't all come with activators. And so this is like the fuel for an engine. When you buy a tractor, you don't get a lifetime of fuel. We have to put the fuel in. These trace elements act as enzyme activators, and now the enzymes within the organism then begin the functioning role of converting these compounds, these elements, into simpler and more complex compounds until we have our plant structure and our plant nutrition. The major trace elements are boron, chlorine, manganese, iron, copper, zinc, molybdenum, cobalt, nickel, and some 60 additional minerals that act as essential or beneficial components for plant function. And again, there's not enough of these to be structural, but these activate the systems within the plant that actually build your structure. Minerals are required for enzymatic processes to build plant structure. Many of these minerals run hundreds to thousands of enzymatic functions, and they're vital for activating the enzyme processes within the plant that allow the plant to take these raw materials, these raw minerals and elements, and put them into plant metabolites that grow and structure everything above and below ground. Photosynthesis is the very first chemical reaction that occurs in these plants with the use of sunlight. 6 carbon dioxide and 6 water molecules through photosynthesis respiration using photon light now creates sugars and oxygen. This is the chlorophyll. The photosynthesis breakdown is the splitting of CO2, carbon dioxide, and the splitting of water, H2O, to recombine into your monosaccharide 6 carbon, 12 hydrogen, 6 oxygen sugars, plus the 6 oxygens. As the plant begins to compose structure, carbohydrates are the first plant primary metabolite, followed by proteins, followed then by lipids, which are our fats and oils. Please note here that carbohydrates are carbon, hydrogen, and oxygen. Proteins are carbon, hydrogen, oxygen with the addition of nitrogen or sulfur. Lipids, again, carbon, hydrogen, oxygen, plus phosphate. Everything here is built on the carbon, hydrogen, oxygen base. Everything. The types of carbohydrates in plants are different carbon chain sugars. The first group is monosaccharides, of which there are 5 groups, 28 sugars, and they range from 3 carbon, 4 carbon, 5 carbon, 6 carbon, and 7 carbon chain molecules. When you look at the molecular structure of every one of these sugars, you're simply adding carbons, hydrogens, and oxygens. And so in our 3 carbon chain group, we have an atomic mass of 90. In the 4 carbon chain group, the atomic mass increases to 120. We're simply increasing the amount of carbons, hydrogens, and oxygens. As plant structure becomes more complex, what God does is take a very simple formula and just repeats it. And so a disaccharide is nothing more than 2 monosaccharides. They're not different sugars. They're combinations of previous sugars. So there are no more sugars or carbohydrates in a plant than what exist in the monosaccharide groups. It's just those sugars are used in different combinations to make more complex carbohydrate structures. So as we look at this, your disaccharides are simply two monosaccharides combined. Oligosaccharides are simply 3 to 10 monosaccharides. As this plant increases its carbohydrate chains, they get longer, they get more complex, and they get larger in size. Polysaccharides are many, many, many monosaccharides combined. As we get into the composition of amino acids, now we're introducing an additional molecule, either nitrogen or sulfur. And so you look at tryptophan, 11 carbons, 12 hydrogen, 2 nitrogen, 2 oxygen. And so as you look at the molecular weight, it's 204. 176 of that is carbon, hydrogen, and oxygen. 28 is the nitrogen component. And the point here is your amino acids are predominantly carbon, hydrogen, and oxygen. Again, everything is built fundamentally in the whole world of plants and food on carbon, hydrogen, and oxygen. We're simply adding a different element or mineral to make a different construction. But fundamentally, carbon, hydrogen, oxygen is the foundation of every plant component. Taking this a step further, let's look at our fatty acids. As we start with our saturated fats and we look at our monounsaturated fats, you look at the construction, it's all carbon, hydrogen, and oxygen, nothing else. You go into your omega-6 polyunsaturated fats. Again, nothing more than carbon, hydrogen, and oxygen. Your omega-3 polyunsaturated fats, nothing more than carbon, hydrogen, and oxygen. And even your trans fats, both trans and cis, are both carbon, hydrogen, and oxygen and nothing more. Your phospholipid structure is composed of 3 components. You have your choline, your phosphate group, and your glycerol as the head. Attached to them are your fatty acids. You have a phospholipid layer on the exterior of the cell and one again on the interior of the cell. As you look at the composition of elements in the phospholipid membrane, you see that carbon and hydrogen and oxygen again are the very dominant structural components, with nitrogen and phosphate being added to change the components within that part of the cell membrane. With the composition of our plant primary metabolites, carbohydrates, proteins, fats, and oils, the plant then continues on into producing plant secondary metabolites. These consist of 4 groups. The first one are alkaloids, and we're all familiar with these. Morphine, nicotine, cocaine, caffeine are just a very few of the alkaloids. And as you notice, all of these are built on carbon, hydrogen, and oxygen, with the alkaloids having a nitrogen component. Terpenoids are the next group, and there are many groups of terpenoids. You have monoterpenoids, sesquiterpenoids, and diterpenes, which are all constructed of carbon and hydrogen. In a second group of terpenoids, you have esters, and you can see again we have carbon, hydrogen, and oxygen. Aldehydes, carbon, hydrogen, and oxygen. Ketones, again, carbon, hydrogen, oxygen. Phenols, the same. They're all composed on this primary carbon, hydrogen, oxygen. As you continue on into the phenolics of the plant secondary metabolites, you can see again, each group is carbon, hydrogen, and oxygen. In the plant secondary metabolites is where you have this incredible diversity of medicinal components. These are nutritional components. When Hippocrates talked about let food be thy medicine and medicine be thy food, the vast majority of the nutrient and medicinal compounds will all be found in your plant secondary metabolites. None of these components can become constructed and functional and complete without the trace elements activating the enzymes that through the plant's own divine intelligence build these medicinal components. In just the terpenoid group, which is one of 4 of the plant secondary metabolites, there have been well over 22,000 different terpenoids identified. Each one of those types of terpenoids has between 300 and 800 different components or constituents in its makeup. So when you do the math, this is somewhere between 7 to 15 million different molecular arrangements from carbon, hydrogen, and oxygen. This is only one of the 4 plant secondary metabolites. So now we're looking at the potential of 30, 40, 50 million different plant components and medicinal components that the plant has the intelligence to make if it has the trace elements to allow the enzymes to do what they're designed to do. It's very interesting to note the process of photosynthesis where we take carbon dioxide and water and turn it into sugar and oxygen. Cellular respiration, wherein our mitochondria now takes the sugars with oxygen, we turn it back into carbon dioxide and water at the time that we produce the ATP energy through our cellular respiration. These 2 processes, one is putting energy together, the other one is taking that energy and releasing it. Again, and you can see it is a perfect flip. Cellular respiration is a perfect opposite of photosynthesis and vice versa. This means that the entire energy structure within a microbe, a plant, an insect, an animal, or a human is strictly carbon, hydrogen, and oxygen based. There's no NPK in this system, not a bit. It's carbon, hydrogen, and oxygen. And that's the critical part of plant nutrition that we're completely missing and we don't focus on whatsoever. Cellular respiration breaks down the sugars and the oxygen and it goes back into CO2 and H2O water. Section 1, Summary. Plant dry matter content. 96% of the plant is carbon, oxygen, and hydrogen. These are 3 atmospheric gases. Carbon is 45%, oxygen is 45%. 90% of your plant is CO2, fixed by microorganisms. Hydrogen is 6% of your plant. Those 3 elemental atmospheric gases make up 96% of your entire plant's dry matter weight. These 3 elements are not even considered or planned for in our fertility model with NPK. Carbon, oxygen, and hydrogen are required at over 30 times more than NPK, calcium, sulfur, magnesium combined. CO2 is the single most important element that our plants need for high yield. Carbon, hydrogen, and oxygen are the basis for not only photosynthesis but also cellular respiration. The plant primary metabolites of carbohydrates, proteins, and lipids, fats and oils, are all carbon, hydrogen, and oxygen based. All of our fatty acids and essential fatty acids of omega-6 and omega-3 are all carbon, hydrogen, and oxygen based. Plant secondary metabolites of alkaloids, terpenoids, phenolics, and sulfonated amino acids are all carbon, hydrogen, and oxygen based. Photosynthesis and cellular respiration are both carbon, hydrogen, and oxygen based.